All right, everybody. So we are going to begin the next lesson in force, which is on Newton's laws. And before we just jump right into Newton's laws, let's talk about some of the famous scientists and philosophers, natural philosophers that kind of contributed to our understanding of how things work in physics dealing with forces. So one of the first people that I want to talk about is Aristotle, who you've probably heard of. He was more of a philosopher, but he was also called a natural philosopher, which generally talked about how nature worked and how things happened. So he had all different theories that not always turned out to be right, but for his time, he was kind of an expert in the idea. And he talked about forces a little bit. And then the guy that is credited with more of what we actually use today still is Isaac Newton. And he was around the 17th century, so the 1600s. And he was probably, again, Aristotle and Newton, both really, really, really smart people. And you can read through those slides of some of the things that they came up with. But Newton was pretty much the scientific expert of his time. So just kind of talking through an idea that sort of started with Aristotle and how he described how things move. He came up with this thought experiment where you have sort of like a bowl and you have a round object like a ball or a rock. And if we drop the ball from this side into the bowl, what would happen to it? So if you let go of the ball would roll down and roll up. And he said, okay, if there's no friction on this ball, and I don't know if Aristotle talked about friction that much, but there was no like resisting forces that would slow it down. What would happen to the ball? So it would start out over on this side, and where would it end up? It would end up on the exact opposite side, and it would basically repeat that process. So it would just keep rolling back and forth and back and forth and back and forth forever. And he talked about like the force of the pull of things that pull things down, which I don't think he called it gravity, but the idea of gravity pulling things down kept this ball in motion. That was the concept from Aristotle. So he said that forces were needed to keep the ball moving. And later on, like centuries later, Newton kind of came across that idea and changed it a little bit to try to prove his way of thinking. And he said, imagine that we didn't have a whole bowl, but we only had half a bowl. And then this section that was flat here was also frictionless. So there's no friction in any of these spots. F for friction, we'll just say lowercase f. So no friction on anything. And he said, okay, well, what would happen if we again started the bowl at the top and it rolled down this frictionless section and then it was on a flat frictionless section? What would happen? And what you would probably come up with is that the ball would just keep rolling. And because there's nothing to slow it down or speed it up, it would just continue to go at that same rate, at the same speed or velocity description, whatever you're using. And that is what he came up with. So Newton said that once the ball's in motion, you don't really need forces to keep it moving. It should just keep moving by itself. So it has this natural tendency to maintain its motion. And that leads us into Newton's law. So that idea, that concept is the first law, and I'll define that in a minute. But Aristotle and Newton had different ideas on it, and that's how science works. Like people have ideas, they generally get accepted for a good period of time until there's some better explanation that covers more information. So Newton kind of changed the way that people viewed some of these things. So Newton's first law of motion, and the laws of motion are universal. So they're supposed to be able to describe how things move and the behavior of motion, regardless of where they are and the conditions that they're in. And Newton's laws work a lot of times really well, especially for everything that we're going to ever encounter in this class. But there are some limitations of it, and Einstein came up with some other ideas later on. We didn't get into Einstein because we don't have to worry about studying him. But his theory of like general relativity and how things move is actually a better descriptor than Newton. So again, as time goes by, people come up with better theories. They have better tools, and you can refine the way that we describe things. So, but Newton's laws work in our normal everyday lives, so we use them still. And Newton's first law here, it says kind of what we were talking about in that experiment. A body in motion stays in motion at a constant velocity. So the ball keeps moving in a straight line, going the same way, at the same rate. And the body at rest stays at rest. And then that is unless acted upon by a net external force. So there's really three parts of this statement that are important. So I'm going to underline the 3 different parts. So the first one is the first part here in red. So it says body in motion stays in motion at a constant velocity. The next one I'm going to underline in blue, a body at rest stays at rest. And then the part that I'm going to underline in black is sort of the kind of descriptor. And it says, unless acted upon by a net external force. So we need to kind of define what that means. So I think we understand a body at rest staying at rest, or a body in motion staying in motion. The third part here says, unless acted upon by a net external force. So net external force, we talked about forces and forces adding together. So if all the forces are balanced and they're canceling out, the net force is 0. If you have an unbalanced force, so there's some amount of force acting on an object and it's not all canceling out, then that force is going to change the motion. So that's what causes the acceleration, which will cause it to speed up or slow down or turn, which are all things that would affect the motion. And this is known as the law of inertia, or Newton's first law. So we kind of discussed those ideas. Here's an idea out of the book. So it says, consider an object that has no forces acting on it. If it's at rest, it will remain at rest. If it's moving, keep moving at a straight line, constant speed. So that's like constant velocity. And they have this example of like they're doing a crash test with a car and a crash test dummy in the car. So so if you think about the car is going to go and run into this wall. The wall pushes on the car and decelerates it. It slows it down. It stops it. And the car stops because the force changes the motion of the car, but the crash test dummy doesn't have a seatbelt on, so it keeps moving forward. So the dummy moves forward until it runs into something and a force acts on it. So again, that example is demonstrating the object in motion staying in motion, that part of Newton's law. The second part, where an object at rest stays at rest, that's really easy. If you have a parked car, parked car is just going to stay there. It's not going to move or change motion until some force acts upon it. Okay, and then again, that's the criteria. So if if the forces are all balanced, they all cancel, nothing's going to happen. But if the forces are unbalanced, then the motion will change. Okay, so some implications of Newton's first laws. This is where it kind of talks about what can happen, and then it also describes sort of the opposite of that, of what can't happen. So if the net force is 0 on a body, so if you add all the forces up and they're all balanced and they go to 0, that means the acceleration is also 0. And that means that the car, it can't turn, it can't speed up, it can't slow down, it can't do any of these things. So so if you are traveling at a constant speed, or if you're stopped or at rest, or you're not turning, then you have no net force on you. But if you are doing any of those things, if you are accelerating, speeding up, slowing down, turning, then there is a net force, and that's okay too. All right, so let's try this one. This is an example question, so I'll ask this as probably the first question in the video. So it says a cart is pulled to the right with a constant speed, or constant steady force. So this is a constant force. And it says, how will its acceleration graph look? So if it's a constant force, and you look at those graphs, so let's just describe what's going on in each of these before we try to answer it. So in this one, it looks like the acceleration starts at 0 and the acceleration is increasing as time goes by. In B, it looks like the acceleration starts at some positive value and starts decreasing as time goes by. And the third one, it looks like the acceleration is some positive value and it stays at that same value. So let me give you a second to consider, if you have a constant force or some steady amount of force, what would happen to the acceleration. So if you had a constant force, would the acceleration be changing, increasing, the acceleration is getting bigger, the acceleration is getting smaller, or would the acceleration stay constant? So let me let you answer that question. And the correct answer is C. So the acceleration is constant because the force is constant. So if you have a constant force, you have a constant acceleration, and that is what's going to happen. All right, so that's Newton's first law. Newton's second law is actually the easiest of the 3. It is the most mathematical, though, so if you don't like math, you might not like it. But it is described on this slide here, which is also in the book. So it says, a force causes an object to accelerate, and that acceleration that it experiences is directly related to the force and directly or inversely proportional to the mass. So let me just kind of describe what this is. So this is A equals F over M. So again, A is acceleration, F is force, and M is mass. So we've talked about acceleration in the previous unit when we were describing motion. Force, we're talking about, it's just a push or a pull. And then mass we haven't really talked about, but mass is the amount of matter in a substance. That's in chemistry. In physics, we talk about it's the amount of inertia that an object has. So if you're more massive, you have more inertia and it is harder to accelerate. If you're less massive, you have less inertia or less stuff to move, and it's easier to accelerate. So it kind of makes sense. Like if you had to push a heavy box versus a lighter box, and you pushed with the same amount of force, the heavier box would be more difficult to move, and the lighter box or the less massive box would be easier to move. So that's kind of the idea. It says the directions of the acceleration is the same as the direction of the force. These are supposed to be arrows above it, so it's supposed to be, these are vectors. So the acceleration vector and the force vector point the same direction. So let me talk about this idea of directly proportional and inversely proportional. So what this means is if something's directly proportional, it means as one variable increases, so let's say we increase the amount of force. So if the force that we're applying to something, we're making it get bigger, then as a result of that increase of force, there is an increase in the acceleration. So as one thing gets bigger, so does the other. So they do the same thing. If we decrease the force, then the acceleration would decrease. So that is a direct relationship. Whatever happens to one variable happens to the other one. So the way that we see this in a mathematical equation, they're in the same part of the proportion or fraction. So like if I put this a over 1, it's still a, it's still a fraction. It's just when you divide by 1, it doesn't do anything. If you see this a and f, they're both in the numerator of the fraction, or the top of the fraction. So if you are in the same part of the equation, then you are directly proportional. So a is in the top, f is in the top, they're directly related. So they follow this relationship where if f increases, a increases. The opposite of that is called inversely proportional. So if something's inversely proportional, we would say like, okay, if we increase the mass, so if we make the mass get larger, then the acceleration would decrease. So that was what I was talking about. Like you're going to push a box with a force, the same force each time, and we're going to make the one box light and one box heavy. The heavy box is harder to move, so it has a smaller acceleration. So that is what's called inversely proportional, or indirectly proportional is another way you could say it. And if you look at them, they're in opposite parts of the fraction. So the a part, the acceleration part, is in the numerator or the top, and the m part is in the denominator. So they're in opposite sections of the graph. So that's really it. It's just plugging in and solving. So if you know the net force and you know the mass, you can get the acceleration, or if you know the mass and the acceleration, you get the force. So it's just like using that formula. A lot of times you'll see it in books, and I don't think your book does it this way, but if you're looking online, or maybe in lessons, it might be F net. So the net force, the total force when you put all the forces together, is equal to MA. That's another way that you'll see it written. The way that it's written here is actually the way that makes more sense, because the force impacts the acceleration, and the mass impacts the acceleration. So these two factors, F and M, are dictating how much acceleration you get. But sometimes problems are set up where you want a certain acceleration and you know the mass of the object, and then you could figure out how much net force you would need to produce that acceleration. So that is another way that you might see it written sometimes. Okay, so let's try this problem real quick. So it says a constant force causes an object to accelerate at 4 meters per second squared. What is the acceleration of the object with twice the mass that experiences the same force? So this one, it seems like they don't maybe give you quite enough information, but that's okay. We'll kind of work through it and it'll be fine. So basically what they're saying is, okay, we have a force that is acting and it causes an object to accelerate at 4 meters per second squared. They don't tell us what the mass of the object is, so I'm just going to make it up, because we can do that because of this proportionality idea. So as long as we're consistent and we do what it says, we should be able to figure it out. So I'm going to say the mass is 1 kilogram. Kilograms measure mass. We'll talk about kilograms and mass more when we get into weight and specific forces. That's the next lesson. So we're going to say the mass originally is 1 kilogram. So if I said this is my 1 kilogram box, and we're going to push it with some constant force. So this arrow that I'm pushing with is going to be the same in both the cases. And because of that, that force being applied to this 1 kilogram box, we get an acceleration in the first case of 4. So that's our first acceleration. In the next one, we're going to have the same force. So we have the same amount of force. So I'll try to draw that the same size. That looks decent. So that's the force here in blue. I'll call that F, and this force in the second situation is the same. And what we're doing is we're applying that force to an object that has twice the mass. So if our first mass, M1, we'll say was 1 kilogram, and we're going to make it twice as big, M2, if we doubled this amount, it's twice as much, it would be 2 kilograms. So we would have 2 kilograms, and I should use the mouse because that'll make my writing much better. Yeah, so 2 kilograms. I was wondering why I was struggling so hard. So 2 kilograms for that. So if I make a box here, my box got bigger, right? So this box and this box, they're not the same. This one's 2. So again, if we have this idea of acceleration is equal to the force divided by the mass, and we're going to make the mass get bigger, the acceleration should get smaller. That's the case because they're in the opposite parts of the fraction. They're inversely proportional. So we can cancel out that it's going to be the same. That's not going to be right. It's not going to accelerate more because the box got heavier. So we're down to these two. And if we think about it, we're basically taking this force and dividing it by 2 instead of 1. So we will get an acceleration of 2 meters per second squared. That is what we should get for that. So that's kind of how that equation and formula works. So we got 2 meters per second squared for that. All right. Forces, we talked about working in direction, so this is just reinforcing that. So like if we had sort of a basketball, the weight of the basketball or the force of gravity is trying to pull down, we talking in this example, so I'll say gravity, FG, they use W, that's okay. They said that there's a drag force, so like if air resistance or something like that, so if the ball's moving to the left, there's air resistance going to the right. So that would be like FD. I always write F and then the thing most of the time in my idea. So this is drag. So the overall effect would be this arrow. So the net force would be the sum of those two vectors. We've done this before, again, with net force and free body diagrams, and hopefully that still makes sense. And the acceleration goes in the same direction as the force. So that's why I left this slide in here to kind of reinforce that concept. All right, let's try another one here and think about the direction of sort of the net force and what's going on. So it says an object is lowered at a constant speed. All right, so it's moving down. It has a velocity down because it's being lowered, so the velocity is down. And it says which of these statements is true? The rope tension is greater than the object's weight. So let's talk about what tension is. Tension is the force in the rope. So there's some force going up, which is in the rope, and we'll call that the tension. What is the force trying to pull it down? That's going to be the force of gravity, right? So there's some gravity force going down. So I'll label that with an FG going down. And I just drew them in their directions. I didn't worry about the sizes yet, but we'll talk about those sizes. That's really what it's asking. And this idea of constant speed is important. So if you have a constant speed, that means this is unchanging. So if you have a constant speed, it's good to know that the acceleration is 0. So if your acceleration is 0 because you have a constant speed, that's what that always happens with a constant speed. That means that your net force, because force and acceleration are directly related, if your acceleration is 0, that also means your net force is 0. So if your net force is 0, what should happen with these two forces? That's basically what's happening. So if their forces, the net force is 0, that means they're balanced. So this amount and this amount are the same amount. So if there was like 10 newtons going up of tension, there would also be 10 newtons going down of gravity. And if they're equal, they just cancel out, and the rope tension equals the object's weight, and that's why the net force would be 0 and the acceleration would be 0. If it's speeding up or slowing down, so like if it's going down and going faster, the force down would be bigger than the force up, because again, it's winning the tug of war. If it was lowering downward, but it was slowing as it went down, the force up would be bigger than the force down because, again, the tug of war. So those two arrows are going against each other. You got to figure out the net force. I was trying to change color and it didn't work. The net force here, which I'm drawing in green, is the difference between those two. So if we had like, so the net force. So if this was, say, 10 going down and this was 2 going up, then this would be 8 going down. And if we flip the scenario over, if we had 10 going up and 2 going down, we'd have 8 going up. And whichever way, that should be a bigger arrow, sorry. Whichever way that arrow points, that's going to dictate the direction of the acceleration, because the net force and the acceleration always point the same way. They agree with their direction. And then when that happens, that's going to dictate how the object is moving. So you would look at, oh, the velocity is moving down and the acceleration is going up or down, and that would have it speed up or slow down because of agreement or disagreement, which we talked about in the kinematics unit. Okay. So they're equal in that example. All right. Forces are measured in newtons. I've said that a couple probably times. To get force, a newton, it's 1 kilogram times 1 meter per second squared. That's equal to 1 newton. That is what we use in physics class. In your everyday life, you probably use pounds. So a pound of force is a typical amount that you would talk about. So like I am about 210 pounds, my weight. So if I wanted that in newtons, I would take that and multiply it by 4.4 newtons. So for every pound, I would multiply that by 4.4. So I'm like 800 and some, maybe 900 newtons of weight of my in newtons. Okay, my force in newtons. So working through second law problems, just to kind of go through one of these again. When you examine the forces, so if we have a force going in multiple directions like this, you got to worry about components. So in a force that acts horizontally, that's the x direction. Again, right is positive and left is negative in the x. Forces in y directions are vertical, and they go up and down. So positive is F force in the y, and a negative in the y would get you a force going down. So you might have to do some trig, you might have to do some cosine sine work and figure things out. I suggest setting up this table. I showed you this table in the last video with some of the problems. So setting up a chart with x's and y's, you draw your free body diagram, you set up this chart, you label all the forces. The bottom row is the net force in the x direction and the y direction. You worry about pluses and minuses and zeros. And then sometimes you'll do some trig at the end with like the Pythagorean theorem if you have like numbers in both of these. A lot of times one will go to 0, so it makes it a little simpler. So that's fine. So let's just try one. So it says a force acts on a 20 kilogram object. So 20 kilograms, that would be the mass. F1 is 200 at 35 degrees above the negative x. F2 is 50 newtons in the positive y, and then finally F3 is 150 newtons at 20 degrees below the positive x. So I'm going to draw that picture first, and our goal of this problem is to determine the magnitude and direction of the net force. So we want to find the overall force, so we're going to use the chart method and figure that out. And then we're going to find the acceleration of the object as well. So we're going to use Newton's second law to help us figure that out. So let me start with a dot for that object. And again, I think I mentioned this before, but you're going to try to draw these arrows so that they make sense in terms of their size and direction. So this says it's 200 at 35 degrees. This is 50 in the positive y, and this is 150 at 20 degrees below. So if we look at these three, the F2 is the smallest and it's supposed to be 50. I'm going to draw it in blue, and it's in the positive y. So I'll just make that and label that F2. All right. And the other ones, if you think this is 50 and this is 200, so this should be 4 times bigger. So if I made this 4 times bigger, that would be good. So I'm going to make it about 4 of these in length, and it should go 35 degrees above the negative x. So above the negative x is to the left, and it's going up a little bit. So I'm going to go back and grab the green color, and I'm going to go, oh, that's not good. Try to make it straighter. That's not bad. And maybe a little bit longer. There we go. Again, it's just a sketch, so I'm not overly concerned about it. So that's F1, and that would be the 35 degrees, kind of above the axis. And then the last one is 150 at 20 degrees above or below the positive x. So it's going down and to the right, and this one's going to be in red, and it's shorter, so it's not quite as big, but it's going down, and it's like kind of a flatter thing. So that might be good. So I have these 3 forces, F1, F2, and F3. The blue and green and red arrows, and we want to know the net force. So when I put all those together, what direction is it going to head? So again, this is where I use the table because I think it's a good way to organize all the thoughts in the information that's provided by the picture and the problem. So we have F1, F2, and F3. And when we add all those together, we're going to get our net force. So we're going to get the overall effect, which is if we just replaced all those forces with just one force, we would get our net force. So So we're going to go ahead and try to figure out what does that turn out to be. So before we get into doing math and doing the numbers, let's go ahead and just do the positives, negatives, and zeros, because I think that is the easiest thing to do to start. So I'm going to put in a positive, negative, or zero based on the directions of the components of these forces. So if we look at F1, it's going left and it's going up. So left is going to be negative in the x, and up is positive in the y. So those are the two directional ideas that it's just positive or negative. For F2, it's going upward, so it's going to be 0 in the x, so I can put it just a 0 in because it's not going left or right, and it's positive in the y. And then finally, F3 is going right, so that's going to be positive in the x, and it's going down, so that's negative in the y. All right, so I would expect, if I was kind of adding these all up, I think there's a bigger force going left than there is right, so I would expect this to be negative for the net force in the x. And the y, when I put all those together, I have 2 going up and 1 going down, so I'm going to think it's probably more up. But we're going to let the math show us that, so I'm not going to write those in here, but that's what I would expect. So I need to do the math that goes along with this. So again, we're going to use the cosine and sine of the angle. So for this one, for F1, it would be 200 cosine of 35. And your calculator is always going to tell you that's a positive number. So that's why I put in the negative here to remind me that it's going left. So that's 163.8. I'm just stopping after 1 digit, so I'm not complicating things. I'm just rounding to the 10th spot. I'm going to do very similar work for the y direction. It's not going to be cosine, it's going to be sine here. So it's going to be 200 sine of 35 degrees. Again, on your calculator, depending on what calculator you're using, you might have to put the order in differently, but you should get, if you do this properly in your calculator, you'll get 114.7. And I have it as positive because, again, it's going up. So those are my numbers there. For F2, I don't have to do the cosine and sine bit because it's only going in the y, so I'm just going to write all 50 here. So that's 50. And then for F3, I'm going to do the same kind of thing with the numbers for F3. So it's 150 cosine of the angle, which is 20 degrees. So if I do 150 cosine of 20 in my calculator, I got 140. I'm just going to round it up to 141. It's 140.95, so we'll just round it to 141, and that's positive because it was positive because it's going to the right. And then we'll do 150 sine of 20 degrees. So I'm going to put that in my calculator, and I got a negative 51.3. Okay. So we have filled in all the information in the chart, so now we just have to add. So we're just going to add going down the columns to get the net force. So I'm going to say negative 163.8 plus 141, and that's a negative 22.8. So the net force goes to the left, which is what we expected. It was going to go to the left. And if we add the y column up, it's 114.7 plus 50 plus a negative 51.3. And that gets you a positive 113.4. So overall, we have a arrow that's going to the left in the x direction, and we have an arrow that's going up in the y direction. So it kind of goes like this, a little bit to the left and a lot more going up because it's 113. So that would be like the y, and this would be the x. So that's the overall force or the net force. Sometimes we use the symbol sigma. Oh, I wrote those in the wrong spots. Let me fix that, sorry. So you saw that I wrote y on the x and x on the y, so let me fix that. So this is Fy here, and this would be sigma Fx when we add up all the forces in the x direction. And the resultant force is from where we start to where we finish. So that's what we're looking for when it says what is the net force. So we're looking for that. And we're going to do a little bit of math for that, and we're going to solve for theta as well. All right. So we're going to do Pythagorean theorem. So it would be 22.8. And if you're going to put in the negative here, you just got to put parentheses around it. So that would be squared. That's the x part. That's this side of the triangle. And then the y part. So a squared plus b squared equals c squared. It's 113.4. I don't have to worry about the positive putting in there, because when you square a positive, you always get a positive. And that's equal to the net force squared. So we're going to do that math and take a square root of everything after we put that in our calculator. So the sum of the forces is equal to, if I do 22.8 squared plus 113.4 squared, that's 13379.4. And we had to take a square root, so I'm going to take a square root of that. And the net force turns out to be 115. We'll round up to 7, and that's newtons. So 115.7 newtons, that's the overall force. That's the magnitude. That's the amount. We're going to solve for the angle by using the tangent. Just talking about this number here should be larger than either of these two, because these are the legs of the triangle. The hypotenuse is always the longest side. For the direction, or theta, we're going to do the inverse tan of y over x. So it's the inverse tan of 113.4 divided by the 22.8. Inverse tan or arctan or second tan is what we're doing in your calculator. Don't worry about the negative in this. We're going to describe the angle in a second, so you don't have to worry about putting the negative in your calculator. It usually messes people up more than it's worth. So if we do that, we get 78.6. It's going to be degrees. And then we have to describe it. So if you look at this, this is going along the negative x, and this is going up. Okay, so when we write out the things, like we say above or below, what are the directions? So we're going up, which is above. So I'm going to write the word above. And then you just list the direction that you're headed, and this is headed above the negative x. So if we look at our picture, this arrow went up and to the left. And that's where, if this was the origin, it would go above the negative x. So that's what happened. Okay, that's just going through a problem. We did a little bit of that before in other lessons, but just reinforcing that I think is good. Okay, so we're on to the last of Newton's laws, and I'm going to try to get through this one fairly quickly. Newton's third law. It's not that bad, but it is kind of a little tricky. So Newton's third law, you probably heard as for every action, there's an equal and opposite reaction. So you're probably familiar with that, but it's not exactly the way that it sounds. So most people think for every action, there's an equal and opposite reaction. They think of that as cause and effect, and it is not cause and effect. It is not one thing happens and then the second thing happens. These two, they're called actions and reactions. They're happening simultaneously. So it talks about the interaction between two objects. So if two objects are touching and there's a force between them, that force is acting on both of the objects in equal amounts, but in opposite directions. So this example says if A, or object A, exerts a force on object B, then B exerts a force of negative F, or in the opposite direction because it's negative, on A. And these are known as an action-reaction pair. We're going to go through a couple examples, and that'll make more sense. The easiest way to always get this right, and you're going to have to do this on your test, you're going to have to identify an action-reaction pair that you see in a picture. So you just need to identify the two objects that are interacting. So there's going to be two objects, two nouns, and then you need to talk about the force as a push or a pull. All right, so it'll be object A pushes or pulls on object B in a direction. So going left, right, up, down, whatever way you see the force acting. Then the reaction statement is just the reverse. So you just switch the object order. So if object A is pushing on B, then B is pushing on A. It just flips it. And then you flip the direction. It still stays a push or a pull. It doesn't change into a different force. You don't talk about A pushes B and then B moves to the right. We're not talking about the motion of B. We're talking about the forces that are acting on the different things. All right. So if we look at this, object A and object B, so it says force of B on A, that's going to the left, and it's got that length. A on B would be force of A on B. That's the maybe reaction pair. So object A pushes object B to the right, and then object B pushes A to the left. So that would be that statement. We're going to practice a couple more. Another idea, kind of talking about this, action-reaction pairs don't act on the same object. So like the hammer pushes the nail pushes on the hammer. They're acting in opposite directions. It's just the interaction between two objects. That's part of it. Okay. Let me go through an example of an action-reaction pair real quick with a situation, and then we'll call it. So let's say that we have a person. So I got a stick figure person here, and they're going to push on the box. Okay. So I'm going to write B for box and P for person, so I don't have to write out all those words. All right. So let's say that for the action pair, or the action of the two in this third law pair, the person pushes. I'm just going to keep it like really grammatically incorrect because it's easier to like think about. I don't know, for some reason it sticks in your head better. So person push box right. So the person is pushing on the box going to the right. And I want you to try to come up with the reaction for what's happening with the box. And if you go back to those rules and think about those rules that we had, it should make sense. So again, these are the two nouns that I just underlined in red. You just switch the order of them. So it would be box, push, because the verb doesn't change. So the box pushed person to the left. So the box is pushing on the person going that way. So they're and they are equal and opposite. That is the key. So sometimes forces are equal and opposite, but they aren't an action-reaction pair. So that can be confusing as well. We'll talk about those situations probably in a different video. But the idea here is that like it is just you switch the order, you flip the direction, and that is it. So you identify the two objects, you flip and switch. That's all it is. All right. So all right, so let's try this one. So it says 10-year-old Sarah stands on a skateboard. Her older brother Jack starts pushing her backwards and she starts speeding up. And the force of Jack on Sarah is, that's what we're going to know. So I'm going to draw the two people. So I'll draw Sarah first. I'll give her some hair. My stick figure of Sarah. And she's standing on a skateboard. So there's the skateboard. And her older brother Jack, so we'll assume that he's larger. So Jack in blue. And I don't know what happened to Jack's waist, but he is going to push Sarah backward. So if I had right as forward, Sarah's going to go that way. So Jack's force on Sarah is going to go like that. So Jack, if I was writing it out, push Sarah. And according to my picture, I have them going that way. And that's going to be the action force. So we want to know what the reaction is in this statement. So the reaction is what we're trying to get. And again, we just have to switch and flip. So we switch them. So it's going to be Sarah, push Jack. And the arrow was going left originally, so it's going right this time. So that would be the action-reaction in this case. Again, action-reaction pairs, they are equal and opposite. So this is opposite. They're not going to be bigger or smaller. So the correct answer is B. That it is equal to the force of Sarah on Jack. That is the right one. Okay, so this is a long video. I apologize for that. Have a great day, and Newton's laws hopefully make sense.